Okay, thank you everyone. Nice to be here. Okay, my name is Wei Chen. Okay, by UTA, now some students they like to call me Jackie Chen. Actually, I'm not Jackie Chen. Yeah. And so I'm going to give a presentation today, what I'm doing at the UTA for the new sensitizers for photodynamic therapy. And I would like to start with a video. Please play the video.
Accidental discovery in an Arlington lab could mark a big change in the way doctors treat some forms of cancer. Gilma Avalos tonight explaining from the University of Texas at Arlington. All new at 10 o'clock.
There's potentially revolutionary research happening inside this UTA lab.
We're using this chemical reaction to make the nanoparticles.
As its name indicates, this nanoparticle is tiny, so small it can't be seen by the naked eye. Tiny but mighty, says its inventor, Dr. Wei Chen.
It is very effective to kill the tumor cells.
Dr. Chen discovered the cancer killer by accident while working on a project for the Department of Homeland Security. The nanoparticle was meant to help with radiation detection, but he discovered it had an additional benefit.
This material can generate toxin to kill the tumor cells.
Not only do researchers say it effectively kills cancerous tumor cells, unlike other treatments, they say the nanoparticle doesn't affect healthy cells.
We see no damage to the normal cells.
Studies the team conducted on animals show healthy cells were not damaged by the nanoparticle treatment, compared to existing therapies where healthy cells were destroyed.
Under the sunshine, they kill 100% of the cells.
Dr. Chen believes it's an improvement on traditional so-called photodynamic therapies. PDT uses light to activate a nanoparticle injected into the bloodstream. It targets tumors on or just under the skin, like skin cancer. It's less effective for larger, deep tumors because the light can't reach those tumors.
But my invention for this material, we can use it for deep cancer.
That's because his nanoparticle is also activated by X-rays, microwaves, and ultrasounds.
The ultrasound and the microwave also can get much deeper than the light.
Dr. Chen says when compared to other PDTs, this treatment is faster, less expensive, and is already showing promise at treating cancers below the skin. He believes this teeny particle could be a huge game changer.
You're saying that this could potentially replace chemotherapy?
Yeah, that is the hope that we are trying to do, yeah.
Gilma Avalos, CBS 11 News.
They believe a combination of radiation therapy and this nanoparticle could one day be used instead of perhaps chemotherapy. And the university obtained U.S. and international patents on that nanoparticle. And while it may be 10 years or something in that time frame before it's commonly used, the researchers are hopeful that it can someday make a difference.
Okay, thank you. So what we're trying to do, we're trying to understand the difference between cancer cell and normal cell, and then design some nanoparticle medicine to kill only the cancer cell but not the normal cells. So there's many differences. One of the differences is called the active oxygen species. And the cancer cell, they have a lot more. So if we add some to the cancer cell, we can kill the cancer cell but without the damage to the normal cell. What we can do that is called photodynamic therapy. Photodynamic therapy is some medicine you need to use light for activation. We can use light for activation. That is the advantage. Then we can use light to control it. For example, if the medicine go to the normal tissue, but if we don't shine the light to the normal tissue, there's no damage to the normal tissue. However, using light for activation also has some issues. We know some light, the penetration is an issue, like the UV, the visible really cannot get very deep into the tissue. So in my research, I try to invent some materials using particularly this nano materials, and this material can activate by the radiation. And in this case, penetration is an issue. Also, really we extend it to microwave and the ultrasound, because microwave ultrasound also can get much deeper than the light. That's the original idea, and that time I joined UTA, and we use the nanoparticle and conjugate to the porphyrin. However, the system is very complicated. And fortunately, in 2014, we invented a new material. This is a new material. And the really good thing for this material, it has fluorescence. We identify the structure. There's a new material. And they're really interesting to me. This new material is, if we use UV for activation, produce RS, can kill the cancer cells. Particularly, even more important, more interesting, when we use radiation to activate this material, it can produce a lot, much more hours than the traditional photosensitizer like a PBIS. So using this material alone, we can use for the deep cancer treatment. We do need some other nanoparticle, nanomaterials. That's the mechanism. I don't want to talk too much about, but we need energy transfer. And this energy transfer, in this case, we need the energy stay in the excited state for long enough. And here we measure the decay lifetime. They really have very long decay lifetime, so they can energy transfer the energy. And here the cell studies, as you see, if we don't use any nanoparticles, and this dose is really low, only 2 grade, they really cannot kill and damage the cancer cell. But if we use the nanoparticle, they damage a lot and kill 100% of the cells. Why? Because a nanoparticle really can target, go to the mitochondria, and mitochondria is the power station for the cell. So really effective because we can directly damage the mitochondria. And also by doing this, also we can reduce the dose. As you see here, from 1 minute to 4 minutes. If we don't use the nanoparticles, of course, 4 minutes is the best, right? Because the longer time to kill more cancer cells. But here we combine with the nanoparticle, as you see, the 3 minutes is the best one. It means we don't need to do 4 minutes. And in this case, we can optimize the dose for the cancer treatment. And this is really interesting because radiation therapy is it's like 60–70% of the market in the cancer treatment. But the issue is the dose higher, really toxic side effect. So here we can combine the radiation and nanoparticle, reduce the dose. This is why I say we can do deeper and better. Yeah. And also our nanoparticle, they can accumulate to the tumor site because due to the size, the tumor, they have cavities. If the particle less than 200 nanometers, they automatically accumulate to the tumor. And here we do the animal studies, as you see here. If we're using the nanoparticle alone or the radiation alone, we cannot shrink the tumor. But if we combine the radiation and nanoparticle, we can shrink tumor. And in the best case, we can totally remove the tumor. Also, we extend to the microwave, as I mentioned in the video. The microwave activate this nanoparticle also can produce the ROS. So in this case, we can combine microwave and the nanoparticle to kill the cancer cells. As you see here, if we don't use any particles, and the microwave in this case really cannot damage to kill the cancer cells. But if we combine the microwave and nanoparticle, as you see in the 10 minutes, then totally damage the cancer cells. Also here the animal studies, as you see, if we use the nanoparticle alone or the microwave alone, the tumors, they continue growth. But if we combine the microwave and the nanoparticle, we can suppress, not that the tumor did not grow until, and in this case, it is really good result. We try to understand the mechanism because microwave used to kill the cancer simply heating. And by adding the nanoparticle, actually we reduce the heat, but we produce the ROS. In this case, we can combine the ROS, that is oxidative therapy, and the heat together to kill the cancer cell. For the cancer treatment, it is more effective. Okay, here we do more about the mechanism, and we found when the nanoparticle get into the cell, actually they decompose and release the couple, and the couple can induce the phenol reaction to produce the ROS to kill the cancer cells. Also, even ultrasound can do that. Okay, here ultrasound can activate the nanoparticle, also produce again the ROS to kill the cancer cells. In this case, we can combine the ultrasound imaging and the treatment together. Maybe you ask me about the toxicity, they come out or not, and we found after IV injection, a nanoparticle, most of them go to the lung, but in 2 weeks they will come out. And in 2 weeks, actually, they come out, we did not see any really damage to the organ, like the lung, the liver yet. Okay, it means those nanoparticle is really biocompatible. Okay, and we will study more about the toxicity. One of the challenging issues for the photodynamic therapy, after the treatment, the doctor will tell the patient to stay in dark for 2 weeks or 10 days. Otherwise, you go out, the sunlight will activate those medicine to damage the skin. And my nanoparticles, we don't have the issue like that because my nanoparticle, we don't have absorption in the visible, in the sunlight, as you see. So we did do the sunlight test, we did not see any ROS produced. So if using my material, my medicine, and after the treatment, you can go out to do whatever you like. And for companies, for the practical application, this is a good deal. This is very important because if we want people to stay in dark, this psychologically is the issue. And for our material, we don't need to do that. Okay. So I think that's all. Thank you, everyone.